is called the interest point detector or interest point detection, and we will discuss specific interest point detector called Harris detector. That was the name of the author who came up with this detector, and then we will discuss this concept of sum of square differences, which is called SSD, and its relationship to correlation. So we have already discussed correlation convolution. In that context, we will talk about Taylor series, which is very useful concept to use lots of different disciplines, and eigenvectors and eigenvalues, and the invariance and covariance. So these are the topics which we'll cover in this lecture today. And so let's ask question: what is an interest point? So interest point is the point which is expressive in texture, and for example, point in which the direction of the boundary of object changes abruptly, as it's shown here, that this is interest point. So this is different from edges. Edges, what if there is a chain, there's an edge, but here there is an edge, but the direction of edge is changing, as you see here, this edge, and then becomes like that, and that is the corner point or interest point. This can be intersection of between two or more edge segments or lines. Okay, so this is the example of an image, and these are the corner points or interest points shown here. There are lots of these which may not be that relevant, but these are the more relevant. As you as a human, when you look at it, you will say these are the corner points, and these are essentially interest points. It's a real image, again, there are these corner points which are meaningful at the windows and doors, but there are corner points at the trees and so on, and those won't be that useful. So we want to discuss how we can write a computer program to automatically detect those. Okay, so this is a little dark here, so let me see what other light I should turn off. This is okay. This is fine. Whiteboard. It doesn't really make a difference. Okay. Anyway, so what the properties of the interest point detector should be: we want to detect all or most of the interest points in an image, and there should not be false interest points, and they should be well localized. So these were similar things we talk about in the edges. We want to localize edges, and we don't want to detect false edges. It should be robust noise. Again, it's the same thing for edges, and it should be efficient detection. So there can be different possible approaches. We can just look at the brightness of image, intensity, and that's what we are going to use. And that's what the Harris corner detector or Harris interest point detector works. So they'll look at the image derivatives. Again, you will see another application of the derivative or differentiation of an image, and that's what we are going to use. Other way will be that actually you find the edges, you find the lines, and you look at the change in the direction of the tangent. And that was the old way people used to do. And actually, I have a paper we did. The first paper I did at UCF was following this kind of approach. So you will detect edges, and then you will find the curvature of these edges, and the rate of change of tangent is a curvature. Whenever the curvature maximum, then that's a chain, that's a corner point. Okay. So why do you want to do these? Interest point detector. Where can we use it? There are lots of application of that. We can do the tracking, because when you want to do tracking, you need to know what you want to track, and these are the good points to track. And these are used for matching two images, finding the disparity. Suppose stereo, you need to calibrate the cameras and find fundamental metrics, motion segmentation, object recognition, 3D object reconstruction, robot navigation, and image retrieval, indexing, and so on. So it's a very fundamental concepts to find interest points, and it has lots of uses, many more than edges. Okay. So, for example, we want to find the correspondence between two images. So this is one image, and this is words. Again, this is a slide courtesy of James Hayes from Brown University. And then we can look at these two letters too, and there's another image, and that's to appear a little differently, and we want to be able to match these images, and the way we are going to do it is to look at these interest points and match them. So here's another example of two views of this same object, which is a face of a person, and these are the points which we want to be automatically able to detect. And this point is similar to point here, or this point is similar to here. So since this is like a two views, so this is the epipolar line, and we are going to talk about that. So match of this should be around here, and similarly match of the green one should be around here, and so on. But main thing is that we have points here, points here. First we want to detect the points, that's what we're going to talk about today. Then later we talk about how to match them. Okay. So then, as you saw photosynth, the first lecture I showed you a demo from Microsoft. So the whole thing is based on finding points and matching points and doing the reconstruction. So there are lots of uses of that. So so the main thing here is that, well, if you are given an image and you are asked, note down the points which you can, you want to be able to recall these points after this image is deformed like that. And most of the time you select the points which are the corners, like these points, these points, these points, this point. And that's what, the main thing is, that even if it's rotated, deformed, you can still say, well, it's the same point, it's the same thing. So that's kind of intuition here. So given these two images, so we will find these points, interest points, key points, corners, there are different names. And then around each of the key points, we will look at a small neighborhood and get some region, and we will normalize this region and get whatever the content is there, what are the gray levels or color is there, and come up with a descriptor, okay? And that descriptor can be maybe a vector, feature vector is shown here. It can be a histogram or something. Then the final thing is that we'll match those two descriptors. So there are two vectors. We want to say, are they the same? How similar they are. So that's the idea of the key point and key point matches. Okay. So goals for key points is that we want to be able to detect these points which are repeatable, which means if we are detecting in this image, and if this rotated version of that, we should be able to detect exactly same point in this image also. They're repeatable. Okay, so this is like a trade-off. So on one side we want more repeatable, which means we want robust detection, and also we want precise localization. And on the other side, we want these to be robust to the occlusion, and they should work with the if there's no texture. Yeah.
So when you're talking about deforming the picture, you're not talking about stretching or I mean, this is just a rotation.
Mm-hmm, yeah.
But could it be also like really deforming it into stretching it?
Yeah. So that's a good question. So see that we are going to talk about that under what deformations this kind of detector will work. So typically, translation, rotation, it will be okay. Scale, it will have some problem, but we'll talk about that. But we want to be able to do these things at least for these simple deformations. And locally, these deformations are not that bad. But globally, when you look at the image, it may be pretty big deformations because it's local operator, so that's also help us. Okay, so that is the detection of interest points, and then it's a description that once we have interest point, then what are the trade-offs? One is that we want very distinct. Each interest point local descriptor should be distinct so that it will help us to match these, which will minimize the wrong matches. If they are not distinct, then it can match the wrong one. On the another extreme, we want these to be robust to expected variations and maximize the correct matches. So these are kind of trade-offs, and that's why it's a harder problem. So ultimately, what we want to be able to do that suppose here is the image of this toy car, and then we have another image where this toy car is there, but it's a clutter. There are lots of other objects. So essentially, we want to be able to take these little patches around these interest points, which are shown here, and say these are the descriptor, and we should be able to match those in this kind of very complex image. Okay, and even though they look very different, we should be able to say the same point, and that's the whole idea of finding these interest points and coming with a good descriptor, which will help us to do that. Okay, so so again, this is another nice slide from James Hayes. Say, look at this image, and where would you tell your friend to meet you? And simply, it'd be easier to say, just make it an intersection of this point, as compared to anywhere, where. So that's a problem. So this is the image from North Carolina. How many people are from North Carolina here? No one. That's bad. How about South Carolina? Nobody. Okay. Anyway, so this is building there. This is the address, and these are the interest points were detected, and there are quite a few of these, as you see, in 9,300. And we will discuss how to get that. What's the process to do it. Okay. So these interest points are called local features. Then around that we have local descriptors. So again, the steps are identify the interest points. Then once we have interest point, then around each one take a window. We will come up with a descriptor, and which can be a vector around here, around there, and then we want to do matching. So it's kind of repeat of what I said earlier. I just want to make sure that you understand. So given these two images, so we want to be able to match these, and based on these vectors, because that's what the computer will see. Okay, so so the goal is that we want these interest points to be repeatable, and so let's look at these two images. These images of the same mountain, and these were the interest points on the left, which are shown blue, and the interest point on the right are shown red. And it's very difficult to match these, right? Because they are at different places. So we won't be able to match those. So that's the thing, because we are detecting these interest points independently. We take a first image, find interest point. Take a second image, find interest point. But then we are expecting that we should be able to match them, and that's a problem. Okay. So suppose we have a point here, and we want to say, which point it matches on the right. So we are ultimately going to look at all possible one, whichever give you the best match, and we'll select that. And that based on the feature vector around that point, which is called descriptor. So if you look at, small neighborhood around those points, which was shown here, and that's where we will come up with a descriptor, a feature vector. And we want to find out that, which one it's closest to. So in this one, we want these invariants. One is invariance to geometric transformations, rotation, translation, and maybe hopefully scaling. Other is the photometric transformations, invariance, which means the lighting changes and maybe camera lens and so on. So that's the ultimate goal. So if you look at another set of these images, and these are the windows shown here. Around that we are getting the descriptor. These suppose are the interest points. Then these are these small windows around these points. It will look like that. It will look like that, and so on, and like that. So now, as you see that some of these are impossible. Suppose if you use that, it's very difficult to, this can be anywhere here, okay? But these may be more distinct, this may be more distinct. So that's the kind of motivation which we have, and we are going to talk about this Harris interest point detector. This is, lots of citation done by these two guys, so I cannot find, I tried, but I cannot find his picture because I'm trying to show pictures for all these guys. So this paper was published in 1988, and probably this is the only paper by Harris. Then I don't know where he is now. He's from England, but sometime you do one thing and become very famous. Okay, so we want to talk about how to detect these corner point or Harris corner detector, and the main point here is that we are going to do this looking at the local window, and then the idea here is that we want to find the corner point such that if we take that local window, which is shown in green, and if we shift it a little bit, then the shifting of any direction of this window should give a change in intensity. So that is kind of motivation for this. If the shift does not make change, which means it gives you change because it's a kind of unique. It has something distinct, and that's what you were looking at. Say, well, if you want to ask your friend to meet with you, then intersection will be very unique, can identify. If you move a little bit, you will lose it. So yeah, same thing. But if change doesn't happen, then you get confused, and that's what we want to avoid. So now if you take a page around here, and the patch or window, we keep moving, and there is no change, okay? So this is a flat region. If you look at this one, now we are moving around the edge, and again, there's not significant change because it's edge, okay? So that is also not good. Now, if you look at this one, if we look around here, which is a real corner, then there's a lot of changes, and that's what we are looking for. That's a good one, and that's a corner, significant change in all directions. Okay, so now let's say we have two objects. One is shown in the yellow, other is shown in the red, and we want to find the corresponding points in the yellow to the red. So now one obvious point is this corner. We can say this corner matches with this, and this is a displacement, and it's pretty unambiguous, very easy. Now if you look at, let's say we take a point around here and try to match on the red object, there are lots of possible places this will match. It can match here, it can match here, it can match here. So that's a problem. We want to avoid that. Or if you take a point inside this yellow and go try to match inside here, again there are lots of possibilities, and that's not good. So therefore this one is the best thing we can do, and the reason is what is called the aperture problem, or the soda straw view. Because see that if you look at the whole thing, this yellow object and the red object, then it's easy, you can find a match. But what you are looking at, the small neighborhood, like you take a soda straw, look at little piece of image, it is very confusing. So that's also called aperture. Like when you take picture, a camera has little opening, it's called aperture. So we are looking at a very small aperture. And this aperture problem we are going to talk about also in motion, which is important. Okay, so now you know already correlation. So we say that we can find the correlation between F and H. F is an image, H is a kernel, and this is a part of the image, 3 by 3 neighborhood. This is a kernel or a mask or a window, and that's the way it works. You find the pixel by pixel product, sum it up, that's called correlation. Okay, just a reminder what we talked about already. Now, so this is the way it's described, and this is called cross correlation because we have F, we want to find correlation with H. It's a cross because they are two different. F and H are different. There's something called autocorrelation. We can find correlation between F and F. Okay, so where we don't use a different mask. We just find itself and we move it. And that's a notion we are going to use in this Harris corner detector. Okay, so now there's a relationship of the cross correlation, autocorrelation, in what is called sum of square differences, or there's a relationship between correlation and sum of square differences. Okay, so what's that? So let's say we have image F and we have a kernel H. What we do, we take a pixel by pixel difference, square it, and sum up all those differences for that 3 by 3 mask we had. So that's called sum of squares difference. Okay, it's a sum. We find a difference, we square the difference, sum it up, SSD. Okay, that's what it is. Now, if you look at carefully here, and so we want to minimize, if you want to say if this, how similar F and H are, then we want to find pixel by pixel difference, square, and sum it up. If the ideally this should be 0, exactly same. But if it is similar, there should be some number. So we want to minimize that. That's what the SSC does. Now, if we expand this, it's a square. It's like A minus B square. So you know A minus B square is what? How does it expand? A minus A square minus 2AB plus B square. Okay, so then lots of people know that. So that's what it is. Okay, so F square minus 2HF plus H square. So that's what we did. This is what you learn in the elementary school. So, you know, there's nothing new here. So now we are going to simplify this, and we are going to say that, well, this F and H actually don't play any role finding the correlation between F and H, because F is separate, H is separate, it doesn't. So we can delete that. Yes? Okay. So then we have minus 2HF. Okay, so that reduces the sum of square differences. Now we can get it up minus, and instead of minimizing, we can maximize. Okay, and the 2 also doesn't make, you know, there's a scale, we can get it off that also. So now it reduces the correlation. See, because we're multiplying pixel by pixel from H and F, and this is the magic. So we started from sum of square differences, we ended up with a correlation. Okay, so it's good, and you can do this, you can explain to your friends. You learned something new today. Okay, so that is your correlation. So correlation and SST, they are related, and they are doing in a way similar things. Okay, so the reason we wanted to do this, then that's what we are going to use. We are going to use SST. So as we talked about, we want to look at the change of intensity for the shift. We shifted, as I showed you, window. Yes.
So correlation gives you a measure of how close two images are.
Yes, that's right. Yeah, how they are correlated. You know? That's what a correlation comes. Yes.
Also, you switched from, it was like H times F?
And yeah.
You switched to F times
It doesn't matter. As we talk about, you know, you can, in correlation, you can do the, you know, commutative association, all these properties are there. Okay? Any other question? Okay, so change of intensity for the shift. So as I showed you that we were shifting these windows and where was the right one, and that's what we are going to do. So we are going to look at an image I, and the intensity value there is IXY, and we are going to look at the another window. We are going to shift by amount U in X, amount V in Y. So that will become the shifted intensity at Ix plus U, Y, V plus V. And we are going to find the SST, sum of square difference, for all these pixels for this small neighborhood here. Okay? So that we want to find. So now that's called autocorrelation, because both cases is I. It's not F and H as well. Okay. So this is a more explanation here. So as you see, we have an image, and we have these points here, and this is another point here. This is another point here, and another point here. So what we have done, we have generated this autocorrelation surface by shifting this thing. And these looks like this. This is a 3D plot, this is like an image. And these are the autocorrelation surfaces using that little shift. And as you see that this one, we are shifting around the edge here. So this surface does not have any unique maxima or minima. It's a flat. We don't know where is the maximum, minimum. That's a problem. We should not use that. Now, you look at here, this is nothing unique. It's very jumbled and it's not good. But if you look at here, this is pretty good. It has a unique minima. And that will be the point which we want to select using this autocorrelation surface. So that's what we are going to do. Okay? So this is a plot of essentially this EUY. So little shift, we compute, little shift, we compute, and so on. Okay, so this is Brooke Taylor, English mathematician, born in 1685, died in 1731. And we are going to use his thing, what is called Taylor series. Okay, so this guy came up with this long time ago, and is still useful. And that's the beauty of science, that the truth is always truth. It remains, doesn't matter your iPhones and you have iMac and so on. It is, we are building your, say, shoulders of all these giants. Okay, so interesting thing about this guy, he had a problem, getting a wife. So he married in 1721 to this lady from Surrey, that's outside London, and but his father wasn't happy, and then this marriage ended in 1723 after she died, and giving up birth to a son, and he also died. It was very unfortunate because his father was so mad. Okay, so then in 1725 married again, and this lady was from Kent. Kent is another city in England, and who also died in childbirth in 1730. But first his father was happy with this marriage, so it was good. So, but his daughter Elizabeth survived, so which is good. So it's good to know a little bit human side of these scientists, mathematicians. So it convinces you that you can do as good work as these guys did, because they are marrying, they are having kids, and so on. Okay, so now the biggest award you can get in England is become the Fellow of Royal Society of London, and it is also very old. So he became Fellow of Royal Society of London in 1712. And another funny story here is that you guys probably know that calculus, it's debated whether calculus was invented by Newton was an English mathematician and physicist, or whether it was invented by Leibniz, which was German. And there was a big fight. And but at that time, the most prestigious society was the Royal Society of London, and then they have to decide that who should be given credit for the calculus. So the Royal Society of London established a committee to look into all these papers, everything, history, and so on. And the committee was basically appointed by Newton himself. And the committee went through its deliberation and all this thing. They wrote a review decision, said this is Newton, nothing to do with Leibniz. And so then the report they wrote actually was written by Newton himself. Then you just give them, just submit that. And then not only that, then when this report was out, then Newton wrote a review about the report, that this is a really good report. So that's a human side of Newton. Okay, so and on that committee, this guy served. So Taylor was on that committee, decided about Newton and Leibniz. So this interesting story. Okay, so now let's say why we want to talk about Taylor. So there's some concept called Taylor series, and which is also fundamental, very, very useful in many, many different things. A very simple idea, and you need to understand once and you will feel very comfortable. So the idea here is that if you have any function f of x, then that function can be represented in terms of value of that function at any arbitrary point a, and it is derivatives. It's a very powerful result. So if you take one point, if you know lots of things about that point, about the function's value, its first derivative, second derivative, then I know the whole function, which is very good. So that is essentially called Taylor series. So which means I can take f of x and represent that in terms of its value at a, its derivatives, first derivative, second derivative, third derivative. This is called Taylor series, okay? And which is, pretty useful. And we are going to use that in the Harris corner detector. So, and this is not true just for single function. Function of one dimension can be n dimension, 3 dimension, 4 dimension. Suppose if you have a function of 2 dimension, as we have this I, which we are going to use in Harris detector. It's a function of x and y. So we want to find the Taylor series of this at xy. As you saw here, the formula is want to find Taylor series of this at a. So first term is value of function at a, then x minus a, then first derivative f, then x minus a square 2 factorial, then second derivative of f, then x minus a cube divided by 3 factorial, and third derivative of f, and so on. You keep going. Okay? So same thing we can do for 2 dimension, and the way it is that the value of function at point where we want to express, which is xy, the first derivative of I with respect to x, and the x plus u minus x. And since it's a function of 2 dimensions, so we have to differentiate with respect to x and then y, and then this, and you just keep going. So as you see, x will cancel, u and v, and this will simplify that. Ixy, Ixu plus Iy v, and we are going to use that. And you can do this, we are going to use this also for the optical flow, the chapter which we will have on the motion, and you can do the very similar thing there. Now this is a function of 3 dimension, x, y, t. So again we want to express this as, we want to express this side at x, y, t. And so value of this function is x, y, t, first derivative with respect to x, first derivative of y, first derivative of t, and then each other term is that x plus dx minus x, y plus dy minus y, and so on. And as you see, they will simplify. And of course on the left side we have this also, so this will cancel, and then this will become fx, fy, ft, and then we can divide by dt, and this becomes dx dt will become u, become v, and t. And this is actually the famous optical flow constant equation. So we're going to talk more about that in the motion chapter, and you will actually implement this. But this is same thing, Taylor series of a function of 3 dimension, Taylor series of function of 2 dimension, and Taylor series of function in 1 dimension due to this guy who are having problem, finding a wife and a kid. Okay, so now we get back to mathematics for Harris detector. So we were here. So we have Ix plus u, y plus v, because it's a shifted version of Ix, y, and we will find a Taylor series of that. Okay, we will find a Taylor series of this one. We'll keep this as constant. And we already did that, as I told you. So it'll become Ixy and Ixu and Iyv, and we'll just repeat this one. Okay? And as you see that we can cancel these, they are same thing. So we will end up like that. U, Ix plus V, Iy. Of course the square is outside, it is there. Okay? Now this we can write down in a vector form, that we have a UV, one vector, other is the I, Y, Ix and Iy. So this is the 1 by 2 vector, 2 by 1 vector. When you multiply, that becomes Ux plus Viy, which is this one. So this is the same thing as here. Okay? So, which is good. That's what we want. So now, so this is a square. So we have this one, then multiply this with itself. So whenever you have a vector, multiply with the vector, so you have a transpose. So that's why you can do that. So if you expand this thing, then what we are going to get will be UV Ixy once, and then transpose of this, which will become Ix Iy, and then UV become, vector like this. So that is the product of 2 of these. And then what we are going to do, that we will look at these. So this is a 2 by 1 vector, 1 by 2 vector. So multiply 2 by 1 vector with 1 by 2, it will become what? 2 by 2 matrix. Okay? And that matrix we will call M matrix. And we can actually take out UV outside the summation, because summation doesn't involve UV, not XY. And that is your M matrix. And that involve the Ix. So if you do that, actually the product, so this will become Ix with Ix, Ix, then we will have Ix Iy, which is here, then Iy Ix, which is here, then Iy Ix, which is here. So that's a product of this, vector with another vector. So that is a 2 by 2 matrix. And these Ix Iy are the derivative. Your favorite derivative, use Sabel, Brevet, Gaussian, whatever you want. So again, we are staying with the derivatives of the image. Okay? So, so that's what we have. So we have this E, which is the error function, which gives us value with respect to shift. And that's what we are going to use. So we have this, and in a way, if you look at this, this is the equation of an ellipse. A circle, then there's ellipse, and these things. It's the equation of ellipse. And so we are going to look at the eigenvalues of this matrix M, which is here. And so the ellipse looks like that, and these are the eigenvalues, lambda 1, lambda 2. And let's talk about, maybe some people have problem with eigenvalues. So eigenvalues, again, a very simple concept, and it's very, very useful. Okay? So eigenvalues, eigenvectors. So simply, eigenvector is a spatial vector if you multiply that vector with the matrix, then you get a vector back in the scalar, which is called eigenvalue. So which is here. So A matrix, we have vector x, multiply A with x, you get lambda x, which means you get a vector x back and with some scalar, which is the lambda. So if that is true, then x is the eigenvector of A. It's a very, very useful concept. You will use a lot. Okay? So lambda is called eigenvalue. X is called eigenvector. Okay? So these, these eigenvectors are the roots of this equation. So how do we find eigenvectors, eigenvalue of a matrix A? You're given a matrix A, you want to find eigenvalues, eigenvalue. So what you do, you take a matrix A, you subtract the identity multiplied by lambda and find the determinant of that and equal to 0 and solve that, find the roots of that equation. Those are eigenvalues. Okay? Very, very simple. Don't get scared. This is very easy. Just believe in yourself. You can do eigenvalues, eigenvectors. It's math, but it's very simple math. Okay? So that's what we have. So then once we have the eigenvalues, then we can find eigenvectors. So let's take an example. This is a matrix A. So these are its eigenvalues, 7, 3, and -1. Okay? And these are the corresponding eigenvector. So corresponding eigenvalue 7, eigenvector is 144. Eigenvalue this one, eigenvector is this one. Eigenvalue -1, eigenvector is this. So, and you can verify that. I'm going to tell you how to get it, but right now you can verify that indeed is true. Okay? So let's look at, first let's verify that. Okay, if I take this vector, multiply with this matrix, what I'm going to get? 1 minus 1, 0, 8 minus, okay, so -1, 8, and 0 will become 7. Yes, the first element. And multiply with this one, 0, 12, and 16 will become 28. Remember, 7, 28. This one, 0, 0, and 28. So what do I have? First element was 7, 28, 28. And what was the eigenvalue? 7. Take out 7. So I have 144. Amazing, huh? It's magic. So it happens. You can do that. And you can verify for other ones. So these indeed are eigenvectors and eigenvalue. So okay, so how do we find the eigenvalues and eigenvector? I take a matrix A and subtract in the identity matrix, I is identity, multiply by lambda, and find a determinant. So this is my A matrix. This lambda, this identity. Identity matrix is a special matrix. It's always a square matrix. On the diagonal you have ones, other elements are 0. Okay? So it's like a 1 in your scalar thing. So we are going to subtract this from that. So we will get -1 minus lambda, 2 minus 0, 0 minus 0, 0 minus 0, and so on. 3 minus lambda, and this is the subtraction. Then you find a determinant. Again, you learned this in middle school. So your determinant of matrix is you take this one, then you multiply this and minus this, and then take one, multiply this, and then take this one. So that's what we have. So we take the -1 minus lambda, and then determinant of this, which is this one, multiply with this minus this, which is 0. And then this will become -2, and then you remove this, and like that, and then this one plus, and like that. So you'll find out that this has these roots, -1, 3, and 7, and these are the eigenvalues. Okay? So once given the eigenvalues, then you can find eigenvectors, and let's say find eigenvectors corresponding to the eigenvalue minus 1. So we're going to use a definition of the eigenvectors. Eigenvector is ax is equal to lambda x. So we can rewrite this like this, a minus lambda x, and we plug in identity. This is x, this is 0, and simplify this becomes like that, and then we get these equations, and from there we have to satisfy that the x2 has to be 0, x3 can be 0, but x2 and x3 plus has to be 1. So which means, it has to be 0. So which means we can select the x1 arbitrarily because there is no x1 here. So let's select as the 1, and x2, x3 from here 0. So therefore this is the eigenvector corresponding to the eigenvalue minus 1, because we have these equations. We have 3 equations here, but actually we have kind of constraint on 2 equations. So x1 we can select arbitrarily any value. So that's where you will find the eigenvectors and eigenvalue. And if you don't want to do that, just go to MATLAB and take the matrix C or A, say EIG, will give you eigenvectors in this matrix, eigenvalue in this matrix on the diagonal. So that's what the concept of eigenvalue, eigenvector is. Okay? So it's very simple. See, the beauty of science is that you learn things very, very intuitive level. They're very, very simple, but you build on those things. You learn these things, you keep building, and you can solve complex problems. But you really have to understand. And that's, at the end, every complex thing becomes very simple, very intuitive. And that's why so many people are still devoted to science. They want to do things, even though it's very hard. Okay, so let's get back to this. So what we want to do, we will look at the eigenvalues of this matrix M. Okay, so we have 2 eigenvalues. So 2 by 2 matrix will have 2 eigenvalues, lambda 1, lambda 2. So what's going to happen that if the eigenvalues are small and around here, so that region we are looking at, that window we are looking at, will be completely flat. If the eigenvalues are large and they are similar, then this is the area where it is a corner that we want to, Harris corner will be around here. If the one of the eigenvalues is very, very large compared to the other one, so that's like an edge. And this is another kind of edge where lambda 2 is very greater than lambda 1. So we are going to play with these eigenvalues to find which pixel should be declared as the interest point. Because we are going to go through each pixel in an image, compute these derivatives, compute this matrix M, look at the eigenvalues, and make a decision. That's basically Harris corner detector. Okay? So what we can do, we can take this M matrix and break it into these S and D matrix, factorization. So which means that D matrix is a diagonal matrix which we are going to look at the eigenvalues, which are the lambda 1, lambda 2. And so that will give us the measure of Cornerness. If you are tired, you can leave. It's okay. So that will give us measures of Cornerness and lambda 1, lambda 2. And the way this Harris define that, how do we decide whether this point is corner or not? So he define a vector R, this is a R, which depends on determinant of D, which is this, and the trace of D, and multiply by some factor K and the difference of these two. So the determinant of this diagonal matrix is actually a product of these elements, and the trace is a summation. So which we can actually do that. It's lambda 1, lambda 2 minus k, and it's a product like that. So that is a R. That's a measure. We are going to apply a threshold on it to determine whether it's a corner or not. And these lambda 1, lambda 2 are the eigenvalues of M matrix. M matrix is obtained by finding the derivative Ix, Iy, Ix squared, Iy squared, and so on, as I showed you here, and which is a lot of fun, which is very nice, because everything is going to actually the derivatives, which is this one, and which you already know how to do that. Okay, so basically you are ready to try this out, which is very nice. Okay, so R depends on only eigenvalues of M, and R is large for corner, and R is negative with large magnitude for edges, as you see here. This is the edge, this is the edge, this is a flat, and this is the corner, and that's the idea. So given these two images, these are at each point we will have cornerness, that R value. Yeah.
So when you're talking about R is small,
Yeah, so again, the threshold idea, so we'll talk about that. So at the end, you have to determine how good corners you want. So at each pixel, you will compute these R values, and then you will apply a threshold, as we did here. So the white ones will survive, but you can change it, more or less, and then these are the points. Now, these are after non-maximum suppression, and these will be the points which are shown here. These are the Harris corners, quite a few of those. Okay, and so then there are other variations of Harris detectors. So there's another paper by Triggs. There they define R lambda 1 minus alpha lambda 2. Zaleski, the author of the book, defined this ratio of lambda 1, lambda 2 divided by lambda 1 by lambda 2. Then Shi and Tamasi, they just look at lambda 1. And so you can plot these, that this is what Shi and Tamasi is going to do, because they just look at lambda 1. And this is one of them is Harris, other is the Zaleski, and tells you that everything is played by the eigenvalues of this M matrix, which we can compute from the derivatives, and then there's some threshold. So I think let me do a couple more, then we'll stop. So one thing here is that what I've simplified, that we have just found the sum of square difference is unweighted, but actually is weighted. So we will apply a weight here for each of the square difference, and this is again the filter. So you will introduce a Gaussian filter or something. So you'll find the pixel by pixel difference. For every pixel you will have some weight, and that weight, if you don't put it as uniform, every pixel is weighted correctly, equally, but this weight can depend on, say, Gaussian. The pixels in the center will be high weight, pixel further away will be low weight. So that was the real one. But you can do the derivation exactly same thing. So this weight can be uniform, so then you don't have to put anything here, or it can be Gaussian. That's what I just told you. So if you put the weight, but you can go through exactly same Taylor series and all this, all that, find a product and matrix, because you just, keep repeating WW everywhere. It's not going to impact anything. So it's just a number. And then you will get M. So which is what ultimately you have. So it's better to explain simple thing first, then you introduce more complexity, and that's what I have done here. So what we are doing here is the image I, and then we look at the window, and then we find the value of this E, and this is the value here. This is shifted, 3, 2. This value, at 0, and so it's intensity, shifted intensity, and the window function, and these are the weights. It's just repeat to make sure that you guys follow, and that's your M matrix, and it is essentially just Ix square, Iy square, and so on. Weight. So here's a good one. So this is the image. So we find the derivative in x direction, derivative in y direction. Then we multiply these two, we get this one. And so if you look at this thing, that essentially this EU, this surface we are getting, this thing is can be visualized that we can approximate by the quadratic function. So and that's where the ellipses come from. So the the idea is that if let's say we take this as a constant, some particular value, then that will correspond to one of the ellipses on the surface. We have surface, 3D surface, but we are taking constant isosurface, isocontour. So these are, in a way, these ellipses. And that's what we originally say. These ellipses, M described by ellipse, and that ellipse is described by the eigenvalues, the major axis, minor axis, and these are the eigenvectors, lambda 1, lambda 2. Okay? So now you can take that image and actually computing the M, and then you can draw these ellipses. And this Professor Hayes did a very good job, and he's showing you how are these ellipses, different shapes, different orientation, and so on. So to give you more understanding. And so the algorithm is that we compute horizontal and vertical derivatives of image, Ix, Iy, compute 3 images correspond to 3 terms in matrix M, because the other repeat, the symmetric matrix. Convolve these 3 images, the large Gaussian window, compute scale cornerness, scalar cornerness, the value R, and find local maxima in that, and that's our corners. So this is an image. These are your derivative. Then you square these derivative. This is Ix square, Iy square, and Ix, Iy. These are terms you're going to use in M. And then you blur it, you apply Gaussian, so it become like that. And then you find the last thing, which is with the eigenvalue determinant and so on. Become this, apply threshold to that. And do the non-maximum separation again here. Okay, so I think, how many more slides you have? Let's go through, I have 5 more minutes. So let's talk about, you asked about the invariance and, covariance. So let's talk about that. So the idea is that, invariance is that if the image is transformed, that corner location should not change, and that's what is required. And the covariance is that, if we have 2 transform images of the same thing, they should be able to match these features. They should be correctly. So as we see here, there's the same object, and we should be able to match those. So now a simple change will be that you take an intensity I and you multiply with some constant, and then add some constant to that. That's called affine change. So let's say what will have impact of that. Suppose if it is just translation, like we add something, then there's no problem, because we are finding derivatives, and we talk about derivatives as translation invariant. It doesn't make difference. Now this is a kind of scale. We are multiplying with this thing. So what's going to happen that suppose this is our first, I, and these are the maximum, and we apply thresholds, so we detected 3. Now say we multiply with some number which is on A, becomes like that. Now with using same threshold, then we are going to get this extra thing. So that, makes a little difference, but the translation won't make a difference if it was just this B. So therefore it is partially invariant or fine intensity changes, which means it's not invariant to the scale. And image translation is no problem. So if it is here, if it is translated there, because derivatives windows are shift invariant, so there's no problem with respect to translation. Image rotation is also no problem because the ellipse remain the same, and we are looking at the eigenvalues of that, so it is okay. So we can find that they will not change because as you see the shape is same. Now scaling, suppose a corner like that. Now you scale. You zoom in or zoom out. Now there will be a problem, and these all will be edges. So therefore, is not covariant to scaling. Okay, so I think this is a repeat, and this is your reading material, and we are done. Yeah, you had a question.
Yeah, you said when we get this extra point in the scaling, that
Yeah.
could be a problem. How about when we're translating and now we could possibly lose a point?
Yeah.
Is that?
Yeah, which is okay because we are talking about translate still within that. Okay. So I think we are done.